Let me.
Let's do it.
All right. So yesterday I told you that if we have and I'm going to start calling them capacitors, which means I have a plate of charge that in comparison to the distance between the plates is essentially infinite. And so the original placement of the first one is here. And so I pull the plate up here. And Mr. Evans, what do I have to do to pull the plate up to there? I have to do work. Well, not if it wasn't charged. Well, you would if it had mass, but we ignore the massive stuff. So if I have a positive charge on this plate and a corresponding negative charge on this plate, the original electric field is pointed like this, right? And there's energy in that. If there's electric field, there's potential energy stored somewhere, right? Because how do I know that? Well, the electric field is proportional to the force that you would put, that the charge would feel. And then force is the negative derivative of potential energy. Right? So obviously, the electric field is associated with the energy stored in this configuration, in this charge configuration. So if I create additional electric field, which obviously I do because the field is constant between two infinite parallel plates, then I have created more energy, which means it required me to do work. And am I recording? Yeah. And if you want to, I don't know, I think it's just the lecture on capacitance, but the MIT lecture where Walter Lewin goes over this, he shows that just by looking at this new area, this new volume in here, you can determine that the new potential energy associated with this new electric field is the integral of 1/2 epsilon naught times the electric field strength squared times the differential volume element. So little dV would be a little tiny volume within that guy. And then I have to add up all the volumes. Okay. Now, dV, the easiest way of dealing with that, and actually, no, it'll be super easy. So the 1/2 is a constant, epsilon naught is a constant, E squared is going to be constant because the electric field is constant within the capacitor. So the potential energy is going to be 1/2 epsilon naught, electric field squared, integral of all the dVs. It doesn't matter how you choose a dV. It could be an infinitesimally thin sheet that is in areal extent the same as the capacitor plate, and then just integrate all those. But what do I get when I integrate all the dVs in this volume?
Just a V.
The volume of that volume.
Wait, is dV voltage or is it?
It's volume.
This is volume. Yeah, we're talking. Yeah, and that's why I misled you about yesterday, which is why I kind of go over this again. This dV is the dV that I'm creating as I'm pulling up the differential volume, right? If I pulled up a macroscopic amount, well, I pulled it up a microscopic dV amount an infinite amount of time.
Wait,
So all I'm saying is that this integral is just the total volume, right? That I've just created.
What shape is that you just made?
It's a rectangular prism.
A rectangular prism.
Yeah.
So basically,
because the area isn't infinite, so it does have an area. I mean, the plates do have an area. It's just that the area we're assuming is much larger than the space in between them, which is why we're allowed to do this. Now, if I knew that area, so this ends up being just 1/2 epsilon naught electric field squared times the volume, right? That volume is this volume. It's a rectangular prism. Any prism is just area of the base times the height, right? Which is why in this case it'd be a length times a width times a height. But usually when we're talking about the areas of capacitor plates, it's just like the area of the capacitor plate. That's it. So the volume in here is just going to be the area. And then what do? Multiply by what?
2.
By this distance right here, which I'll call D. Right? Isn't the area of this capacitor plate times that distance there the volume of this region?
Mm-hmm.
Yeah.
Wait, okay, so is that just U? Is that just...
This is the potential energy that I've stored in here. Just in this part.
Yeah, okay, that's what I was asking.
This is the configuration before. Now I'm doing work, storing an additional potential energy, and that will be here, yes.
Okay.
And again, it's just the electrical potential energy stored in this configuration. All right. Well, let's remember some stuff. Charge density is a charge per unit area, right? So I can write charge as a function, or charge is equal to sigma times the area. The total charge on the plate, if you know the density, you just multiply that density times the area, and it gives you the total charge on it. And remember that potential difference is the negative integral from a to b of E dot dr. The magnitude of it is just that without the negative, so irrespective of which direction you actually go. But the electric field in there is going to be constant, right? And so if I decide, let's say I decide to integrate from here to there. So my dRs are all going to point up. And so my final will be here. So when I do that integral, this will be position B. This will be position A. So final minus initial if I'm going this way. Notice I'm being consistent with the direction of dr, which is a vector, and where I start and end. Okay? So the potential difference is going to be, and what E dot dr here is actually going to be negative E dr, right? Because I'm going the opposite direction of the electric field. You can go the other direction too. I'm trying to just prove a point here. Make a point. And so that's going to be the negative integral of this, but the electric field is constant, which makes capacitors, parallel plate capacitors, so nice. The electric field is constant in there. Times the integral from A to B of dr. And what do I get when I add up all the drs?
R.
D.
D. Well, it would be R if I called that R. But it's going to be D, right? When I add up all the infinitesimally small displacement vectors, their length is going to be the total distance, total plate separation. So this is just negative E times essentially final position minus initial position, sorry. But it ends up being this, right? Many students just remember that the magnitude is just E times D. Because what that sign tells you, it just tells you, well, which way did you go when you did the integral, right? And it doesn't really matter in physical reality. You have the same voltage there, right? Regardless if you do the integral this way or that way. You're going to get the same voltage difference. You're going to get the same energy storage. So a lot of students, including myself, once I kind of understood this, I just remembered that in parallel plate capacitors, the voltage is always equal to the electric field times the plate spacing. Okay? Plate spacing meaning the spacing between the plates. Notice I started here just because if I had started when they were actually together, then the charge would be flowing through them. So I start here and create some additional electric field. Where does the electric field actually come from? In the manufacturing process of the capacitors, they have to do some work to separate some charge, which in effect would be just like the work that you would have to do in just pulling charged plates apart, fighting the electric force between them. So all that to say, this is a version of this equation, which written like this is on the formula sheet. This is how it's always going to be for a constant uniform electric field for 2 points separated in that field a distance d apart, a radial distance d apart. If it's a capacitor, then it's just E times the separation distance, the plate separation distance. So that's something that I'm going to use to simplify this result into something that might help. What do you say?
I asked for the negative one, but it's just a magnitude, I guess.
Yeah, let's just talk about the magnitude. Because again, what the potential here is higher than the potential here because we're closer to the positive charge. So the potential difference, VB minus VA, will be positive, but VA minus VB will be negative. So it depends on what direction you go, but you know that the potential difference is going to be the same. You know that capacitor is going to be at a certain voltage. So it's just the magnitude, a lot of times. Right? when we do integrals with like weird charge distributions, we gotta be a little more careful. But if you just got a capacitor, really we're dealing with the magnitudes of things. Or at least it makes it a little easier. Okay. So with this guy, and this guy being, this is a volume here, right? That's why I put the delta there. Right? This is a volume. The volume, did I already put that in there? Yeah, what's the volume?
DA.
Where's my blue?
DA.
The volume is D times A. I'm going to write A times D. Otherwise it looks like a, yeah. It looks like an infinitesimally small area vector, right? Okay. So let's make some substitutions here. Let's call, how do we do this again? We call 1/2, I'm going to keep there. Sigma over epsilon. Oh, we need another one too. I'm sorry, guys. We're going to need this guy. We're going to need this guy. We're going to need this guy. And we're going to need the electric field for a capacitor. Right? Mm-hmm. So I'm going to plug that in for one of these E's, just one of them though, because I'm being clever. I'm going to leave the other E, the other electric field alone. But for one of them, I'm going to sub in sigma over epsilon naught. And then for the volume, I'm going to put A times D, and now I don't have to worry about having two different V's anymore, because I replaced that. Right? And so I've gotten rid of epsilon naught, right? And then, I'm an idiot. On my notes, it said skip a few steps and arrive at this conclusion. That was not smart. Let's see. We need to get Q in there. So I don't want area to be in here. So I'm going to write this as the area is Q over sigma. Yeah. A lot of times this is how theoretical physics works. You just mess with it. Not that I know much about that. I've never done it. But.
Oh, so sigma.
So U is going to equal 1/2 electric field times, oh, that's just sigma times Q over, oh, so say, yeah.
Prescription EV squared.
No, because this is E.
He plugged in for one.
Oh, I got you.
Yeah.
So just one?
Yeah,
Yep.
yeah, so, because I'm being clever.
Oh.
Being clever.
He's being clever.
So U equals 1/2 times the electric field times the charge times D. So I think I'm getting there.
Then you have to plug in E again.
And then delta V is E times D. So I see in
Where's delta V at?
Q, yeah, QED.
Maybe we should use like
Yeah.
R stuff.
Big D.
Well, no, I just want to see the E and D right next to each other, because if I see that, then that's potential difference, right? So the potential energy then becomes 1/2 Q times the potential difference between the plates. Right?
Yeah.
That's on your formula sheet.
Oh, okay.
That's the potential energy stored in a capacitor.
So smart, Mr. Green.
Oh yeah, because I did this, of course. Yeah.
Can't believe you invented it.
I didn't watch Walter Lewin do this and just write it down like he did. I totally did this myself.
Yeah, but you figured it out.
Can't believe you invented that. That's
I know. I'm pretty smart. What can I say?
Wait, so we're gonna have questions like this?
No, I'm showing you where this comes from.
Oh,
You're not going to have to deal with this
You're
equation.
deriving it. You're deriving it.
Yeah, and I didn't even show you how this comes about. But it's not something that you wouldn't be able to handle. But it's just not necessary. This technically isn't necessary, but it's good to know where equations come from.
Wait, okay,
So this, if you have a capacitor, like this guy, if you have a capacitor, UC tells you the amount of the amount of energy you can store, the amount of joules of potential energy you can store.
okay.
So, and that will be, this guy is rated for 30 microfarads capacitance. What voltage? Oh man, it's
So weird.
something set 170 volts AC. So it's rated to run at a certain voltage, so when it's fully charged, it'll have that much charge based on how much energy it can store. Right? So that's what capacitors do. They store energy, electrical energy. When you store them, you charge one side of them which drives charge off the other one. That's why they get oppositely charged, right? And then there's going to be a potential difference across those. There's going to be a voltage across those capacitor plates, which is why if you were to connect them, you'd get electric current to flow because that's what drives electric current. And the two things you need for electric currents are a voltage difference and a path for the electric charge to actually move, like a wire. Okay. All right. So this is on the formula sheet, but it looks like this.
It's like so you wouldn't have any.
It's 1/2 Q delta V, which also equals 1/2 C delta V squared. That's what's on the formula sheet. And this is what we talked about yesterday. Started talking about, but then I realized I could do a better job. So this tells you the energy stored in capacitor. And how do you get this? Well, it comes from the definition of capacitance, which we'll talk about now.
Hey, Mr. Graham.
Yep.
So if they have the same voltage, then nothing happens, right?
Right.
Well, how does that work with like two batteries? Like you connect them to each other and they spark. Alright. Like if you have like two like batteries, like car batteries, and you connect them to each other, why do they like create a spark?
There will probably be a slight voltage difference between the. I wouldn't recommend doing that though.
Yeah, I know.
You know, when you average day, you connect two by car batteries.
I remember trying to jumpstart my car using my brother's car before, and I put the terminals on the wrong leads on the wrong terminals,
Oh yeah.
and I fried his stereo system. It was not good. He was mad at me.
Did you have to pay him?
I had no money.
Two different.
No. No.
He's using it as an example, right?
No.
Well, what it does is just runs current through.
Okay. So this is on the formula sheet. This deals with charge, voltage, capacitor energy, and also C. C is capacitance. It is a new quantity. And the way it works in that equation, well, it works because it's just simply defined as. Is it on the formula sheet? Q over delta V. Is that what it looks like on the formula sheet?
Well, no, it's
Or is it-
delta V is Q over C. That, but
Okay, yeah. On the formula sheet, it says the capacitor voltage is charge divided by capacitance. But the definition of capacitance is Q over delta V. It's kind of an abstract concept, but it tells you essentially how much charge you can store on a conductor. Specifically for the useful purposes for a capacitor, a parallel plate capacitor. But a capacitor doesn't need to be a parallel plate capacitor. We'll do this problem soon, where it's a capacitor made by a charged sphere surrounded by a oppositely polarized spherical shell. That's a capacitor. It's going to be able to store charge. The Van de Graaff generator is a capacitor. It has the ability to store electric charge. Right? If you have the ability to store electric charge, you have a capacity to do so. It just turns out that you don't have a very high capacity to store electric charge. That's why when I stand on the thing there, make my hair stand up, and I fist bump someone, you feel it, but it's not gonna hurt you, right? Because I don't have a lot of capacity to store charge. This actually doesn't have a lot of capacity to store charge. Even though it gets up to 400,000 volts, it doesn't have a lot of charge on it. So you're not going to get a lot of charge being pushed onto you by that voltage, even though it's so high.
So voltage is like difference between. Yeah, maybe that's no question.
The thing, if you this is a negative. This pretend it builds up a positive charge, and I release a positive charge from right here. Okay, it's going to move from where it has high potential energy, which is here, to where it has low potential energy here. If I take that potential energy and divide it by the amount of charge there, then I negate the necessity to have that charge, and now I have a potential, which tells me how much potential energy I would have if I did put a charge Q there. And then same thing happens. Well, as I go farther away, where the object, if it was there, it's going to lose potential energy, so we have less potential energy here, then we have less potential here as well. So from a spherical charge distribution, the delta V is always negative as you move away. But then it's always positive as you move forward. And so that's why the negatives trip up a lot of people when they start studying this, But often negatives, or where negatives crop up, they're dependent on your choice of direction whenever you do your integral. The reason why when we have a charge distribution and it's always from r to infinity, well, we can go from infinity to r, but then we'd have to slap a negative on the front because we know that E dot dr, if the electric field is doing the work, is taking the charge and taking it from r and throwing it to infinity, right? So it depends on which way you go, whether it's positive or negative, for a lot of this stuff. There are times when it's obviously very important, and we'll stress those times when we see them. But for now, and note that this is the capacitance. This charge is the charge on the positive plate. What was that? Is that you?
Yeah, it was.
Right.
Who's this guy?
That's the charge on the positive plate. And this is the voltage. I'm going to start using this word. This is the voltage across. How do you spell cross? Is it just one C?
I think it's 2.
No,
It's
not.
one. It's one.
No, it's not.
It's good thing you don't teach English.
2 C's and 1 S.
Why would anyone want to teach English?
That looks weird.
I agree entirely.
Voltage across the capacitor plates. As you'll see when we start doing circuit labs and you have to start making voltage measurements, you got to find where the capacitor is in the circuit and you got to measure the voltage across it. Okay? If you just take a voltage probe and put it here, it's not going to say anything. If you take this other voltage probe and put it here, it's going to say 0 because it's 0 potential difference. So you got to go across the circuit element, across the battery, across the light bulb, across the inductor, across whatever device you're talking about. And so that's the voltage across. If we have a single battery over here, this guy's at the same voltage as the positive terminal of the battery, 1.5 volts for most. And this guy's at the negative terminal voltage. What's that voltage? You would think so, but by definition and just by construction, it's 0. The negative terminal of any battery is just defined to be 0 volts. So really, it's the potential difference across the battery that's 1.5 volts. Right? It's not the electric potential; it's the potential difference from the positive to the negative terminal is 1.5. In that coordinate system, we can just define the negative one as 0, in which case the positive one would be 1.5, regardless of what the actual difference is. Or the actual values are, I should say. All right. Cool beans. There's just some basics here. Charge per volt, or coulombs per volt, is the unit of capacitance. Coulombs per volt. So it's hard to interpret this unit. Unit is coulombs per volt, which means if I increase the voltage, what happens to the capacitance? It's keeping the same amount of charge. It actually decreases, right? So if you don't try to wrap your head around it too much yet. We'll be elaborating on this soon. But yeah, I will tell you this. Capacitors are designed to work at a certain voltage. So usually this is the thing that's going to be fixed. The capacitance is going to be fixed. And what changes is that you just either load it or unload it. Right? The capacitors that are in your charging blocks, they're always being used. They're always they're constantly discharging and recharging. They're never fully discharging, I don't think. But they're always doing something. But the capacitance of that capacitor will not change. As we'll see. We'll see why. The potential, it's going to be designed to work at a certain potential. If you hook it up to a different potential, it's not going to work the same. What's going on out there?
Lunch.
Okay. What is dictated by what does change is going to be the charge that gets loaded on the capacitor. Okay. So let's actually talk about the Van de Graaff. I'm going to charge it up.
Let's go.
Oh! Got a
That's
whole
like
bunch of them.
5 of them.
There's no way.
They all got tangled though.
No way they're all gonna go up.
Yeah, they will. They all got tangled though.
Oh, they're untangling.
So I charged it.
Are they? Because they're separating. Are they separating because they're repelling each other?
But then they got tangled, so they're... So that guy's got a charge on it, right? It's storing electric charge. It's acting as a capacitor. And it obviously has the capacity to store charge because we see that it's storing charge. And it's long-term storage because it's turned off right now, but it still has it. It will lose it over time, obviously. Oh, dang it. It will lose the charge over time, obviously. Mainly because of polar molecules in the air that just kind of come on and just grab extra electrons off. But we know that guy's got charge. We know it's storing charge. So let's calculate its capacitance using this definition. So capacitance is going to be the charge stored on that Van de Graaff generator divided by its potential. I'm just going to put its potential because where are we referencing this to? Delta V. For a single charged object, the only place we can really reference it to when we're talking about the potential on the surface of that thing is infinity. And beyond. No, just to infinity. Can't go beyond. So delta V, if final V is infinitely far away, is just V, initial voltage. And that's what we're interested in. We want to know the capacitance of this conductor. We're talking about charge that is stored on the surface of this conductor. And that charge on the surface of that conductor will be Q. And the voltage will be the voltage on the surface of that conductor where charge Q is located. All right? So we have an equation for voltage, don't we? For a point charge, because right off the surface on that point charge, the voltage is going to be 1 over K times Q over the radius. And I'm going to do capital R because that's the radius of the actual Van de Graaff. What is that? R over K. Right?
Yes.
This is one time where they like to say this, because that's going to be 4 pi epsilon naught times R, right? 1 divided by K is 4 pi epsilon naught. This is the capacitance for a spherical capacitor. Oh, I didn't define the Coulomb per volt thing. I kind of just went up right over that. This gets a name. We'll come back to this in a second. Sorry. This gets the name. This is the definition of a new unit. Does anyone know? Starts with an F.
Frequency.
No, that's a quantity.
Force.
You guy's name was Michael?
Faraday.
Faraday, good. That's a farad. Which is, the unit is just capital F.
I don't know how I remember that. Isn't there like a
Michael, Faraday's law is one of the 4 Maxwell equations.
Yeah.
Farad? Is it Farad?
It's farad. You can call it farad if you want to be weird. All right. So that's what. So the capacitance, this guy right here, and this is the capacitor for my pool pump motor. I've had to replace it several times. It's 30 microfarads. So this guy can store 30 times 10 to the negative 6 coulombs per volt of electric potential across the plates.
30 micro.
All right. This is the capacitance for a spherical capacitor. What does it depend on? Radius of the spherical capacitor. What else? That's it. This is important. The capacitance of at least a spherical capacitor, we'll see if it's the same here, is determined by nothing else but its geometry. Just the geometry. How it's physically constructed determines the capacitance. Okay?
So the bigger it is.
Didn't you say spheres are also variable capacitance?
The larger R is, the larger the capacitance is going to be. Yeah.
I'm assuming we're about to find out why.
Yeah, so let's say, so this guy is 30 microfarads, this capacitor right here. Let's say I want a spherical capacitor that will have the same capacitance as this 30 microfarad capacitor. So the capacitance is 4 pi epsilon naught times R. However, I actually know K better than I know epsilon naught. So I'm going to say R over K. Right?
Yep.
So the radius is going to have to be K times the capacitance, which is going to be 9 times 10 to the 9th, times the capacitance, what did I say, 30 microfarads?
Yep.
30 times 10 to the negative 6. That's going to be 270 times 10 to the third, right? Or 270,000 meters, or 270 kilometers, which is what, like 160 miles?
That's a big sphere.
Right.
That's how big the radius has to be?
Yeah. If I wanted,
Really? Oh my God.
if I wanted this guy to store as much charge as this guy, it would have to have a radius of 80 miles, 100 miles,
That's crazy.
on the order of 100 miles. Okay. So yeah,
It's a huge.
this thing charged can wreck your day. That thing charged can make you jump a little bit if you're not expecting it, right? So just for comparison, if you want if you want a 1 farad capacitor, and I have some of those too, they're actually smaller than that. A 1 farad capacitor made out of a sphere, it would have to be almost 6 million miles in circumference. No, in radius. Yeah, that's radius. So that's much, much larger than the Earth. Much larger. And I have 1 farad capacitors that are smaller than this. Hence, parallel plate capacitors is where it's at when you're talking about capacitors. They don't make spherical capacitors to actually do anything, right? All right. So notice that just came from this definition, right? That definition. So that's good. Now I can start on my journey to this type of a capacitor using the Van de Graaff generator. So let me charge it up. Let me make sure everything's neutral first. It's not a charger, see that? These are really good, except that one's broken. But.
Oh wait, you got a broken one?
Was that?
No, that was the old one. No, the other.
No, we got 2. No, that one over there is another one of these, the one that doesn't have the dome on it.
It's broken.
Because the plastic piece that holds it up was dislodged, and then the belt on the bottom, the spool, is broken.
Did you break it?
Just like that, I pulled it out. That was the first one I pulled out, and I couldn't do anything. Anyway, so I'm going to charge this guy. And I got this guy. This guy's grounded, okay? So I'm going to start this guy up. And let's sorry. So let's look at the size of the spark. Hopefully this works. You see it?
No.
You guys see it? Get it charged up. Yeah, move if you need to.
Oh.
Watch this guy. A little different, huh?
Yeah.
You guys get up if you need to come look.
It's moving the ball.
Whoa. Oh,
Yeah, that's substantially bigger spark, right? Something's going on. Something's different here.
Wait, so what if you put your hand
I bring this guy in.
Because the radius is small.
That's the shock that I get. That's not that bad. If I was to get this shock, I would feel that. I would feel that. Okay. So what's happening is that when I bring this guy close, it's changing the capacitance of this whole thing. It's funny how that all.
And like you can see like depending on the size of the shock how much they go down.
Like a bauxite's
Oh, yeah.
large and big.
Oh, so that's so cool.
All right. So what's happening here?
Magic.
Well, yeah. Aside from that,
I'd make a camera.
be cool to go back in time with just basic science stuff from today and be
You
like,
want to go back in
look
time
at-
to Van de Graaff.
Shock everybody.
you have to get someone to ride a stationary bike though. I wonder how well that came out on the video. Probably not well. Sorry, Alex.
What you get for getting COVID.
For what?
That's what you get for getting COVID.
Oh. We miss you, Alex.
No, we don't.
She probably thinks you actually don't like her.
We wouldn't miss Ryan if he wasn't here.
No, we wouldn't.
That's for sure. I'll go on the record. All right, so here's our Van de Graaff generator. And if I just turn it on, it builds up charge. This particular Van de Graaff actually builds up negative charge.
Do some build positive?
Yeah,
Did the old one build positive?
I think so. I'm actually going to figure that out at some point.
Wait, suppose in the Van de Graaff.
So this is going to, it's going to have, it has a capacity to store a certain amount of charge, right? And that capacity is 4 pi epsilon naught times the radius. It's not a lot of charge that it can hold. It looked like some kind of weird bug. That was awesome.
Phenomenal.
Look at it. So they're still charged.
Mm.
Isn't that NATO?
NATO?
NATO? NATO's not NATO. Okay. So we got minus Q, total charge minus Q. And think of the potential. It might be easier to think in terms of positive charge. Let's pretend it's got positive charge, okay? Otherwise, you got to do the negative switching in your head if we're dealing with electrons. So let's assume that it's positive Q just to make this work out a little easier. So we're using the old Van de Graaff. Okay. The potential at point P is the work required to bring a charge there divided by that charge, right?
Mm-hmm.
That's the definition of electric potential. So the higher the potential, the more work I got to do to bring a positive charge in. That's why I said make it positive, because if it's negative, then we got to flip it. But it's the work per unit charge. All right. Well, let's now bring in this other guy that's grounded. So I connect this, pretend that's a circle. So I connect this to a ground wire, which that's the schematic symbol for a ground wire. And what happens to that conductor? Remember charging by induction. The same thing is happening here. What is this positive charge doing?
All the negatives go.
No.
The negative charges on this guy want to come to the surface because they're attracted to these ones, leaving a deficit of negative charges as we go this way, so we pull up negative charges from the ground, right? So this guy is going to build up a negative charge. And then if I disconnect the ground wire, that negative charge is now stored. Does it require more or less work to bring a charge from infinity to that location now? Less. Right? And there's a couple ways of thinking about that. Well, this guy's going to fight me, but this guy's going to help me.
Yep.
Right? Yeah, so it's going to require less work to get there.
Wait, is P in the way? Or what, like which way is it?
No, P's just in the space between them.
Is between those two?
The two charged spheres, the Van de Graaff and the other guy.
Okay.
Yeah. The other guy is just a ball on a stand, right? That's then connected to the ground. And so what that means is that you actually reduce the electric potential at P. Right? The electric potential gets reduced there. Well, if I have a fixed amount of charge, let's say I charge the Van de Graaff to where the things are sticking up, and then I turn it off so it keeps that charge. This guy attains essentially the same charge by pulling up extra electrons. So this guy essentially becomes negative Q in a perfect world. And if this happens, then the potential at this point, I'll say like this. The potential at point P goes down. Why does it go down? Because it requires less work to put charge there. which means less work per unit charge to put charge there, which means less potential. But in my equation and if though I have fixed the charge there, I turned off the Van de Graaff, I'm not allowing charge to go on or off. If I have fixed the amount of charge there, what have I just done to the capacitance of my capacitor? I've increased it. Which means now I can actually store more charge on it. Right? So this is essentially what we do. I turn this guy on to charge it. Did I stick to... No. We want to make sure it's charged. And that's what's cool about these guys. They tell us if it's charged. Or you can just shock yourself, and that way you find out if it's charged too. So I charge this guy up. And I turn it off. So it's got a certain amount of charge. And now I move this guy close. I have not close enough to get shocked, but I just move it close to where I have now decreased, especially right between them, I have decreased the potential at those locations because now they're oppositely charged. So one fights me when I try to push charge in, but the other one helps me. So I've decreased the potential, so now I've got the capacity to put more charge on by the definition of capacitance. Right? Because I got the same charge on it, I didn't see any sparks, so no charge actually flowed. And so what I've done, I've reduced the voltage between them and around them as well, but it really happens in between them. I've reduced the voltage, so I've increased the capacitance, so now when I turn it on again, I can get more charge on the Van de Graaff than I was able to before. The more charge I get, the bigger, thicker the spark I get, right?
If you have it right there and you like charge it up so you increase its ability to, its capacitance, and then you move it away, you move the ground ball away, with that.
Like after this guy's gotten more charge, then it'll be kind of overcharged and it'll just kind of leak off into the environment pretty quickly because it'll be kind of pushing it off, Yeah, that's a good point. So does that kind of make sense? I push this guy closer, I increase the capacitance, but I also decrease the electric potential. If I decrease the electric potential, what happens to the electric field?
It decreased.
Am I jumping ahead? I might be jumping ahead. I'm jumping ahead. I'm sorry. Okay. So and we saw the difference, right? Hopefully we saw it. We'll see it again. When I turn this on, again, I'm a capacitor. I get kind of polarized when I get close to the conductor, but charge doesn't flow through me the way it flows through this when it's connected to the ground wire. And so, yeah, I kind of increase the capacitance a little bit, but not much. And not to an amount to where when it discharges, it's going to have a big, thick shock, right? A thick spark. For that, I need to significantly increase the capacitance. And now I can store more charge. So when it discharges, I see more charge being discharged as a much larger spark. You get shocked before your hand gets there. It feels different. It punches a little harder. I think it feels like it. Yeah, I can feel it tingling after in the spot. So yeah.
Why isn't doing it anymore? You broke it.
I broke it. Interesting. All right, cool beans.
Cool rice.
I think those beans need to be warmed up.
What's the rate at which it increases as like the distance between the two?
We're gonna get into the math of that now, and for a little bit longer.
10 more minutes.
Remember, as Brant pointed out on the formula sheet, it says that the potential difference equals Q over C. Just realize that is the definition of capacitance written in a different way. When we're talking about capacitance, it is the charge, by definition, on the positive plate divided by the voltage across the plates. So if I wire a capacitor to a 1.5 volt battery, the side of the capacitor, the plate that is attached to the 1.5 volts will be at 1.5 volts. The plate that is attached to the 0 volt point, which is the negative terminal, will be at 0 volts. So the potential difference across the plates would be 1.5 volts. And the charge on the plate will be just the total amount of charge on the positive plate, because what is actually the amount of charge stored in a capacitor? What's the total amount of charge here? Zero. Zero net charge. So that would be useless to talk about a capacitor with the total charge. So it's just by definition the charge on the positive plate. So if I say I have a capacitor that's storing 3 microcoulombs of charge, well, that means there's 3 microcoulombs on the positive plate and negative 3 microcoulombs on the negative plate. Okay, it's just nomenclature you got to be aware of as we go and start talking about this stuff. All right, so let's talk about, real quick, and we'll end with this. This is, again, a spherical capacitor configuration, not useful. It does aid. You do get a pretty significant increase in capacitance whenever you do something like this. And the effect would be greater if I had another sphere about that guy's size at the same height, so they're like right next to each other. Not close enough to really spark though, but you got what I'm saying. But again, this is not a convenient. This is convenient for learning the physics, but for actually using capacitors in circuits, you never use ones like this. Never. So let's start our journey into actual useful capacitors.
Yeah, I'm getting ready to pass down. Useless.
What's that?
Nothing.
What'd you call me? Okay. Now, I will note, whenever I charge a capacitor by putting it on, let's say it's an uncharged capacitor first, and then I wire it in to a battery, and this is 1.5 volts and 0 volts. What actually happens, and it's even weirder when you get into the quantum nature of it, but we don't do that in this class. What happens is that electrons move from the negative terminal and load onto the positive terminal, right? And let's say that 6 of them did that. It's probably going to be more than that. Maybe significantly more. But let's say 6 electrons did that. Well, what do these electrons do to electrons on the plate above?
They push them up.
Push them away, right? Away, going this way. And so when that happens, we get 6 extra protons up here whose electrons have left there. Okay. Capacitors do this naturally, right? How can we use just the positive charge? What if the bottom one has a different? But no, it will be the same. These capacitor plates are very close together. Whatever charge the positive plate attains, it's going to drive that much charge off the other plate. I'll tell you this now. Anyone done an engineering class where you deal with circuits at all?
Yeah, we did rocket engineering.
So conventional current goes which way?
He doesn't
I don't know.
Huh?
It goes towards the negative.
It goes from positive to negative. So that's what we will use when we talk about electric current. And since electric current starts with the letter I, we get the symbol I for it.
Wait, you say positive to negative?
Goes from positive to negative.
But why did you?
And then it goes from positive to negative. That's the current direction. When they figured this out, they knew there was 2 different types of charge. So Benjamin Franklin called one positive and one negative. It was Benjamin Franklin. That's who we have to thank for this.
Thanks, Ben.
And he called the one that doesn't move, stop looking out the window. He called the one that doesn't move the positive charge, and he called the one that does move the negative charge. Did they know anything about protons and electrons back then?
Nuh-uh.
No. This is 1700s. When was the electron discovered?
1800s.
I think it was the late 1800s. Proton, not even until the
1800s.
People learn about that in chemistry.
I forgot.
The electron.
Rutherford got the nucleus, but that was before the proton and the neutron. Yeah, it was fairly recently in the grand scheme of things. Compared to when this stuff was decided, yeah, we didn't have any idea what carried electric charge. So they just guessed. And when they started doing circuits, they still had no idea what carried the electric charge. They just knew it existed and it flowed, and that they had this potential difference stuff, potential energy stuff. They had it all worked out before they even knew what was responsible for it. It's pretty impressive. But they called this conventional current. They just assumed it's the positive charges that move. And then it was discovered after this had been common practice for a couple 100 years that no, it's the opposite. It's the electrons that go the opposite direction and then drive electrons off this guy. They're the mobile ones in electric circuits. But they didn't know that at the time, so they had a 50-50 shot of getting it right, and Benjamin Franklin got that wrong. And because we are totally open to change, they changed everything to compensate for now the direction of electric flow. We actually now know they didn't change it. So conventional current, if you're an electrician, you still assume that current goes from positive to negative, even though we know it's the opposite. So that means we're using broken physics, right?
Yes.
Yep.
Might as well drop the class now.
If you're ignoring mass, which we can do for the most part, negative charges moving this way, identical to positive charges moving this way. It's the same thing. It's the same thing. Same effects. If they had to change because of those discoveries, they would have. They didn't have to, so they didn't. Because everything still works the same. But as physicists, so your typical engineer will know this, but they won't think about it too much because it's not part of their job. By the way, your typical engineer knows more about the practical application of electronics than your typical physicist, in my experience. The physicists can talk about the theory and Maxwell's equations and all that. The electrician's like, yeah, I can wire a house, you know. And, yeah. So if you want to become an electrical engineer and start your own electrical company, if you're successful, that's a good way of doing it. Anyway, bottom line here, what I'm trying to get at is that if you load a certain amount of charge, stop, that's gross. If you load a certain amount of charge on one capacitor plate, it's going to, by its very nature, create the same but opposite charge on the other capacitor plate. If I put 6 coulombs worth of electrons here, I will drive 6 coulombs of electrons off the top, leaving me with oppositely charged but equal magnitude charges on the plates. All right? Okay. With all that being said, let's talk about these guys. A capacitor plate in general. We're going to make a little discovery here. It'll be cool. So I'll call the top one the positive one. Let me do the same way I got here. Top one will be the positive one. Bottom one will be the negative one. Remember, we got an electric field in there. Jacob, please. Got an electric field in there. Don't forget about the electric field. I have a positive, I put a positive charge here. So plus Q. And that Q is going to be sigma, the charge density, times whatever area that plate is. Because this is what happens when we charge capacitors, I will have minus Q on the other one. Sigma times the area, same area. Is it exactly the same? Maybe not exactly, down to the number of electrons, but close enough. All right. And so I want to talk about the capacitance of this capacitor. It's going to be the charge divided by the potential difference across the capacitor. Well, the charge on this capacitor, again, it's 0, but when I do the math, I just use the charge on the positive plate. That's going to be sigma times the area. And as I told you before, you might want to commit to memory, the magnitude of the potential difference between capacitor plates is the electric field of the capacitor plate between the capacitor plates multiplied by the distance, the plate separation distance, which in this case is just this distance. And we also know that the electric field is what in a capacitor?
Sigma over epsilon naught.
Sigma over epsilon naught. So that means I'm going to have I'm going to have sigma times the area over D, and then times this guy but flipped, right? Sigma epsilon naught. right? So sigma cancels. So my capacitance is the plate area times epsilon naught divided by the plate spacing. This is important. Look at that result. There's something special about that result similar to our spherical capacitor.
Oh.
What determines the capacitance of a capacitor?
The distance.
The area.
Which are descriptions of the, starts with G, field of mathematics. It's the geometry of the capacitor. It was the same with this guy, right? You want a bigger spherical, you want more capacitance with a spherical capacitor, you got to increase its radius. You got to get big. You want it to hold as much charge as this guy can, you got to make it, what was it, 270, 100 miles, 180, whatever it was. I forgot already. You got to make it big. But you can get much better capacitors.
Yeah, you can make the distance like super small.
Yeah. These distances are usually fractions of a millimeter. Very tiny distance. So that you make this super, super, super tiny and you get the capacitance to go up. Which is why you need a really good insulator between them though, because if you're getting them that close together, the electricity really wants to go from one to another, so you got to prevent that with an insulator. But again, function of the geometry only. You manufacture capacitors to do certain things. You need it to do a certain thing. That dictates what geometry you must construct that capacitor using. And again, these guys, they're hard to take apart. I started taking apart one at home and I was making a mess. I'll try to get that done. But essentially, it's two capacitor plates that are foil sheets with a piece of paper, a high-tech insulating paper, between them, and then you roll it up and then put it in the cylinder. And that's all a capacitor is. And just about every electronic device that you use, any large motor, it's got a capacitor in it. Your air conditioners have a few of them in there. That's what I would do if I had an iPhone.
Does this have a capacitor in it?
I would smash it on the
Does it
table.
have a capacitor in it?
Oh, I don't. Probably.
I have a question.
Will blow up.
All right, that's it. Bye, Alex. Subscribe, Alex. Subscribe.